Swayam Prabha. Digital India. Educated India.
So, I would mainly talk about separately excited because I don't want the field also to get modified. So, separately excited, I will be able to keep the field completely separate and the armature completely separate. The two controls can be completely decoupled from each other. So, separately excited DC motor fed by a rectifier. So, we are looking at, let us say, a fully controlled single phase converter. I am just taking the single phase converter. Three phase would almost work similarly. And then I am going to have the DC motor drive here. Right? So, this is going to be my supply, and let me assume maybe this is positive and this is negative during positive half cycle, and I am going to have a field which is excited by a constant excitation current, IF. So, the flux is not going to change at all, right? So, what I get as EB will be proportional to the speed because the field current is a constant, right? So, I will have this as plus and this as minus, right? Normally, the rating of the DC motor drive will be given, maybe 220 volts, 10 ampere, you know, whatever is the output, vagera, vagera, all the details will be given, because of which you should be able to calculate the back EMF constant. Back EMF constant calculation is not a big deal, right? So, if I am given, for example, 220 volts, 10 ampere, maybe 1000 RPM, right? DC motor drive with maybe RA value is also given. So, with all that, you should be, let us say RA is 1 ohm, for example. So, you should be able to write whatever is the output. It's not a big deal because you are going to write basically 220 multiplied by 10 minus 10, that is, this is IARA, will be equal to 210 volts, which is the EB rated. And if 1000 RPM is your rated speed, you can always calculate what is the back EMF. And if I know 210 volts is the EB multiplied by IA will give me the power that is developed internally, and then you might have to subtract the mechanical losses. So, you are just recalling 203. So, that is how you would be doing the whole thing, right? If I want to run it at the rated speed, maybe I will have to apply 220 volts. If I want to run it at any other speed, then how do I calculate the voltage to be applied and the firing angle? That's all is the matter with fully controlled rectifier. So, if I say that my back EMF constant happens to be, that is KE happens to be 210 divided by 104.72 radians per second. I am converting 1000 RPM into radians per second. So, this is volt second per radians, right? So, if I have the back EMF constant and if you are given what is the AC supply, maybe AC supply is 230 volts, right? So, if you are given 230 volts 50 hertz supply or 240 volts 50 hertz supply, whatever, right? Then you should be able to calculate what is the firing angle if a speed of 700 RPM is to be achieved at 50% load torque, then alpha equal to what? This is the kind of question typically you may be able to, calculate for. So, in this case, if it is 50% load torque, hopefully, neglecting the no load current, I can say roughly the current is 5 ampere. 10 ampere corresponds to 100% load torque. 50% load torque is always proportional to field current and armature current. Field current I am keeping as a constant. I am not touching the field current at all. So if I want 50% of the load torque, I should have basically 5 ampere. So I should be able to say at 50% load torque, IA equal to 5 ampere. RA anyway is 1 ohm, that is given, right? 700 RPM, at 700 RPM, I should be able to calculate what is EB. You guys know how to calculate it. Whatever is the back EMF at 1000 RPM, which was 210, you can multiply that by 700 and divide by 1000. So you should be able to get that value, right? At a constant excitation. Everything is at constant excitation. So I'm going to get this as the back EMF. Once I have the back EMF, all I need to do is to add IA-RA drop. That will give me the terminal voltage. So I should say at this operating point, terminal voltage will be equal to EB 700 plus IA dash RA. Let me call this as IA dash. IA dash is 5 ampere. So I should be able to calculate exactly what is the value of terminal voltage. And this terminal voltage, if I say it is fully controlled converter, I should be able to write this as 2 Vm by pi cos alpha, provided, what is the condition? 2 Vm by pi cos alpha, is it valid all the time? Yes. For a fully controlled converter without freewheeling diode, 2 Vm by pi cos alpha expression is valid only when? Yes? Come on. You guys have listened to fully controlled converter for so long. Tell me. At what point this particular expression is valid? You integrated from alpha to pi plus alpha. That is when you got this expression. What does it mean? Continuous conduction. Thank you. That is continuous conduction. Only if the conduction is continuous, this particular expression is valid. So if I don't give continuous conduction, you can always say the question is ambiguous. So unless I say it is continuous conduction, if it is, whether it is continuous conduction or discontinuous conduction, if I say there is a freewheeling diode, then at least you can say it is integrated from alpha to pi, right? So if I am talking about fully controlled converter without a freewheeling diode, I have to specifically say it is continuous conduction. So I should say assuming continuous IA. I have to say I am assuming continuous armature current through the DC motor. Otherwise, it is not going to really make any sense to use this particular expression. This expression is not valid if there is discontinuity. I have to know where the beta value is, and then I can integrate only from alpha to beta. So it is not really correct to apply this expression for anything else. So if I am given a firing angle with continuous conduction, I should be able to decide the operating point and vice versa. If I am given a speed and torque, I should be able to definitely get what is the value of firing angle if, I am knowing the motor parameters. I should know the motor parameters. If I don't know the motor parameters, I would not be able to do anything, obviously. So I should know what is the RA value, what is the kind of back EMF constant it has, and so on and so forth. Only then I should be able to get this whole thing, right? Is this clear? This is a typical DC motor drive control problem. You should be able to do the same thing for 3-phase as well. For 3-phase, only thing is this expression, whatever we have got here, will be replaced by 3Vm by pi cos alpha, where Vm is line peak again, right? If I give a semi-control converter for 3-phase of course I have not still done. Single phase, you have to change the expression. That's all is the difference, right? And you guys should know how to draw the waveforms also for these cases. I don't think it's a big deal now that you have known all the rectifiers, right? Only thing is we have not talked still about when alpha becomes greater than 90, which hopefully I will take up, because I hope so that you will have questions. If not, we can discuss that. If you have questions, we'll discuss the questions what you have. If not, we'll have to look at what happens when in the same motor drive, if I make alpha greater than 90, or the speed becomes greater than whatever is supposed to be its no load speed. What happens? We can discuss it a little later. Okay, so what is the application of a feedback diode in an inverter? How does it function? That is the question Gantavya was asking. So let us first of all look at the inverter circuit. I am going to show it with an IGBT, right? So this is one, and I am going to have a load connected here. So we are going to have one more device like this. Let me call this as 1 and this as 1 dash. And similarly, when I want the current in this direction, this is the way it is. And when I want the current in the opposite direction, I'm going to have one device like this and one more device like this. So this is 2 and this is 2 dash, and I'm going to have the current somewhat like this. I'm going to complete the circuit now. So this is how it is as far as an inverter is concerned, when I want to convert DC to AC. So this is the DC supply. Let me call this point as A, this point as B, this point as C, this point as D. So when 1 and 1 dash are conducting, I'm going to have from A through 1, through C, D, and then through 1 dash back to the DC supply. That's how it is going to be. And when 2 and 2 dash are conducting, it will be just the opposite. So let me first of all draw the kind of waveform that we are going to get when 1 and 1 dash are conducting. I am drawing basically the load voltage. So I am saying VCD. That's what I am drawing. What is the voltage across CD? I am drawing. So when 1 and 1 dash are conducting, I am going to have, if I say this is VDC, I am going to have VDC coming up right across CD, because I am assuming that the other two devices are ideal. They are not having any drop. So I am going to assume that it is going to be somewhat like this. And then after that I am going to have a voltage which is somewhat like this. So this should be plus VDC and this should be minus VDC. This is the way the voltage will be. If I have a resistance load, I will have the current exactly following the voltage. There is no difference whatsoever. Because of which, I will have essentially 1 and 1 dash exactly stopping the conduction at this point. If I may call this as 0, pi and 2 pi, because I am converting them into AC voltage. So this is how it is going to be. But if I am going to have an RL load, inductive load, right, R and L, then maybe the current would have started from some value, I don't know, I'll have to check. But even initially if I talk about when the circuit was dead, the current would have increased until this pi, because L di by dt equal to V minus Ri. That is the way it will be. Depending upon what is V minus Ri value, I'm going to have definitely, the current increasing further and further. Anyway, the inductance would have built up some energy. So, I would have actually maybe the current going somewhat like this. It would have increased until here. But the current cannot come down abruptly to 0. If I switch off 1 and 1 dash, if there is no other path available for the current, because the current is flowing in this direction, it can flow only through these two devices. If I turn them off, if I remove the gate pulses, both of them are going to turn themselves off right away. This is having inductance. If I try to bring down the current to 0, di by dt is literally infinity. Even if I is only 2 ampere, dt is literally close to 0. So I will have di by dt, because of the denominator being very, very small, it will reach infinity. If it reaches infinite value, this open circuit voltage here will be enormously high. Which means I'm going to have both these devices facing the brunt of the inductance stored energy abruptly trying to collapse. So, these two devices will immediately conk out. If I try to put a circuit like this with RL load, and if I try to turn off immediately the inductance load current, then I am going to see that these two devices can conk out. So, to avoid that, I might like to put a diode called a feedback diode, which will come exactly in anti-parallel for each of these. So, these are all called feedback diode, which come in anti-parallel. Now, the current had been flowing like this. Now, if you look at this diode, right, and this diode, they are, conducive for the conduction in the same direction. But only thing is that, please note that this voltage source is connected exactly in the opposite direction to that of how it was connected with 1 and 1 dash. Because if you now look at the path is going to be somewhat like this. It's the same current, all right, but this current is going to go like this, and it is going to get into the positive of this particular battery. Please note, this is completing the path using this diode. So, you can see that the current flows again in the same direction, but if you look at it from the battery's viewpoint, the battery is not supplying it anymore. It is rather taking the energy which was stored in the inductance. Right? So, if you look at it, this positive now is connected to D through the diode, and this negative is connected to C again through the diode. So, there is a reversal of polarity as far as the load voltage is concerned. So, the load voltage will still be negative when feedback diodes conduct, but the current here is going to start coming down. How fast or how slowly it comes down depends upon what is the kind of source voltage I have had, and what is the kind of Ri drop I have had, and what is the kind of inductance value I have had in comparison to the resistance. All these things dictate how much of energy would have been stored in the inductance. So, I am going to have this. Now, the negative voltage is applied, so it will obviously start increasing in the opposite direction. And again, it will start, this will be the kind of current waveform, exponential rise and exponential fall. That's what you would see normally in the inverter circuit, in an RL circuit, basically. So, I should say, if you talk about the devices that conduct, from here to here, it will be 1, 1 dash. Whereas from here to here, if I may call this as D2 and this as D2 dash, this will be D2 and D2 dash. And from here to here, right, I should have had the other two devices, that is 2 and 2 dash until here. And here the corresponding D1 and D1 dash. So obviously this current should have started somewhere from the negative side. Although I have shown it as though it has started from positive, it should have started from the negative side. Because that current must have been inverting its polarity. It was flowing like this and then it is going like this. So I should have drawn a replica here too. So here I should correct it as though it is starting from somewhere here. Something like this. Not this one. This is not correct. Right? Yeah.
How do we make sure that these diodes are forward biased?
Inductance stored energy will make sure of that. If inductance energy had not been there, I don't have really the requirement of the presence of the diodes at all. The inductance is basically making sure that the current continues in the same direction. When it is making sure that the current is continuing in the same direction, automatically di by dt is in the opposite sense, because of which you will have a reversal of polarity of the voltage. The moment you have a reversal of polarity of the voltage, the diodes will automatically take advantage of that. That's how it is. So how long this current continues in that direction itself, it is continuing from here to here. That duration is dependent upon how much of inductance energy stored is there. How much of energy is stored. And that is going to forward bias the diode. That energy, as long as it exists, it will forward bias the diode. The moment it is not sustainable, the diodes will be reverse biased, the current will come down to zero. So all of them happen naturally because of the energy stored and the energy is given back to the battery.
Like, can there be a case like choosing some values of inductance, like the inductance energy is not